Good morning. How is everybody today? Bright-eyed and bushy-tailed? Okay, well, first and foremost, is there anything you want to look at or any questions you have from what you were playing with or some of the homeworks or looking back over your tests or anything like that? Got a no, a no, and a no. Okay. Good. If anything does come up, let me know.
For the final, because the final is accumulative, how much of what we just did do we need to know everything going forward? Or
Yes, forever and ever, actually.
yes, that's what I was hoping for. This is why I love math.
Yep. It is fun. We do get to be one of the only classes where you constantly have to remember absolutely everything you were ever taught.
You do. I know.
Yeah.
It's crazy.
It is. That doesn't happen in like history. If you're taking a class on like Civil War history, they're not going to suddenly ask you a Pilgrim question.
Nope.
But yes, the final often includes things like particularly quadratics. They come up everywhere. But take these 2 points, make a line, all that kind of absolutely.
Fun.
I'm glad you think so because some people get frustrated by that. So.
Oh, I'm starting to understand math better.
So we were talking yesterday about polynomials in general, and there are a couple of things about polynomials, good generalities, actually not even generalities, good properties of polynomials that we want to become accustomed to. So I'm going to not write this in standard form. I'm actually going to write it in reverse just to maybe show a point I want to make. But we certainly know what the graph of a constant looks like. Say we've got p of x equals 5. Now this is a polynomial. It's an extremely boring polynomial, but it is a polynomial. It is that 5x to the 0. And if we did try to graph that, it would just be that nice straight line at 5. So doesn't have any turning points, doesn't go up, doesn't go down, a very boring little polynomial, but it is a polynomial. If we put actual x terms on this, so let's say we add 2x, still a polynomial, and still, as polynomials go, fairly boring, but it does have a quality to it that it still doesn't turn, but it does have an increasingness or a decreasingness to it. So this we would refer to as certainly a first degree polynomial. It doesn't have any terms. So I'm going to say, make a chart here, degree, turns, and the other one I want is x-intercepts. So the constant, the 0th degree, let me actually put that in here, that 0th degree polynomial, just the constant, had no terms and it didn't have any x-intercepts. It was just that line up here. Our first degree polynomial here still didn't have any terms, but it does have that one x-intercept. It does have that x-intercept down there. So one x-intercept. Okay, if we expand that a bit and say make this a quadratic. So let's say we make it negative, let's just say negative 1x squared. That becomes a second degree polynomial. And we certainly know what quadratics look like when we graph them. Oops. That's okay, I can fix that. We know they look like our nice polynomial, our nice parabolas. Now, I've drawn this parabola facing upward, and that's kind of our typical parabola, but we know that that negative there is going to turn that around, right? It is going to make it face down instead of up. So we really should have it going that way. And it has one turn in it. And it does have, in this particular case, it does have two x-intercepts, but we know that they don't have to. We can have a parabola that only hits once if it comes down here and bounces off the axis. It can have just one x-intercept, or if it was, say, down further, down here, it could have no x-intercepts. So this x-intercepts, we're going to change it from how many x-intercepts to it that has to as many as so many x-intercepts. So 2 is the most it could have. There's no way we could have this parabola have 3 or 4 or 5 x-intercepts, but it might have less than that too. Is that fair? All right. So that's kind of should be our very familiar territory. If we keep going here, though, let's say plus 4x to the third, this pattern should continue. This is a third degree polynomial now. So instead of turning once, a third degree polynomial is going to turn as many as 2 turns. Now again, I say as many as. We can have just a basic x to the third does have that kind of one inflection point in it, as you remember from your 3.5. So if this wiggle is reduced enough, it will turn just that one little slide. But it can have as many as 2 turning points. And for x-intercepts, it can have as many as this 1, 2, 3 x-intercepts. It can have less, say just, again, the normal x to the third with no other things on it, has just that 1 x-intercept. It could have 1 x-intercept by doing that. But it's interesting to note that it has to have at least 1 x-intercept, because it does go from these lower values up to higher values. Get that out of my way. What do you think would happen if we put in, say, negative 2x to the fourth? Take a moment, kind of follow the pattern, and decide what you think that fourth degree polynomial will look like.
Is it going to have 3 turns and 4 intercepts?
It will. It's going to have as many as 3 turns and as many as 4 x-intercepts. That's the most dramatic it can be. And if we look at, where to start, like if it was a parabola, we'd start up at the top here and go down to make a parabola. If it was a line with a basic line, we'd start at the bottom and go up. The third degrees started at the bottom and went through that oscillation. So I want to take just a minute and talk a little bit about how we know where we start and where we stop in these. What's governing the overall shape of these is that lead term, that largest term. This was a line when it was just x to the first. As soon as we put that negative x squared in there, the shape changed and became a quadratic. As soon as we put that x to the third in here, it stopped being a quadratic and started being a third degree polynomial and looked like a third degree polynomial. The rest of these just cause the specifics of where it wiggles, but it behaves in that third degree manner. Now that we have a fourth degree, that fourth degree term is going to be in charge of this thing's overall behavior. The x to the third, the square, the x to the first, the 5, they're all going to affect where exactly the details of those wiggles occur. But that x to the fourth is going to control the overall behavior. That's, again, why we call it the lead term, because it is the one in charge. So normally, disregarding its coefficient for the moment, if we put in either big positive numbers or big negative numbers into that x to the fourth, the even power is going to make those values come out positive, come out to be big, large positive numbers. You put in a big positive, its fourth power is a big positive, so will be big positive. You put a big negative number into x to the fourth, and it's going to still be a big positive. So it kind of wants to come down here and do those 3 turns you mentioned with 4 intercepts. But what's going to change that in this particular example? That negative. Just like the negative on the x squared made us face downward instead of upward, that negative is going to take our normally opening upward fourth degree and instead have it open downward. Seem reasonable? So if we were to keep going here, I want to throw another negative in there. I like them. So let's say negative, let's say 3x to the fifth. It's probably pretty clear now what this chart is doing. We're going to have as many as 4 turns, 1 less than the degree, and as many as 5 x-intercepts, the same as our degree. So if we tried to draw what that would look like, we'd look at that lead term. The 5th degree, just like the 3rd degree and even the 1st degree, 1st degree, 3rd degree, and 5th degree, they all want to go from one extreme to the other. They all want to go either from low to high, or if the lead coefficient is negative, like a negative slope forces us downward, a negative lead coefficient flips them upside down, makes them go from large positive to large negatives. So because this is a fifth degree with a negative lead coefficient, we know our end behavior is going to be up on that side, down on this side. And then in between those, it's going to wiggle. How much it wiggles depends on how much it wiggles and where it wiggles, depends on all these other terms. It is quite possible that we have a fifth degree that just comes down, does a little oscillation, and keeps going down, a very kind of minimalistic x to the fifth. You know, with all those other terms in it, I wouldn't expect that to happen. But it could have, you know, a couple actual intercepts. And then, okay, that would be kind of like a third. It could have another little bump in it. So if this bump was more extreme, it would give us the other two intercepts, but it wasn't extreme enough. So we only got 3 x-intercepts instead of the possible maximum at 5. Without going in and analyzing all of the other little details in here, we don't know exactly where and what those intercepts are going to be. But we do know, as a fifth degree polynomial, we're going to start that way, end that way, and there's going to be some wiggles in the middle with as many as 4 turns and as many as 5 x-intercepts. Questions about that before we take it a little further?
So just to clarify, if it's negative, that means that it's ending in down towards the negative infinity of the y axis or the y values. Is that correct, or is that not?
Depends on what you mean by ending.
It continues in a negative, in a decreasing direction
As the x values increase?
as the x values increase.
Yes.
Okay.
And one of the things you'll often see is it'll say as x heads towards infinity. So as x heads off in this direction towards infinity, the function values head toward what? Well, here, well, let's pick this one. In this one, as our x headed towards positive infinity, the function values headed towards positive infinity. As the x headed toward negative infinity, end behavior here, as we got towards the end of the axes, in this one, as the x went towards negative infinity, the function values went towards negative infinity. Oops. If we look at, say, well, even this x to the fifth we have up here, that x to the fifth went that way. So as x went to positive infinity, for this one, the function went towards, little arrow, went towards negative infinity. As x headed towards negative infinity, the function values headed towards positive infinity. So you'll see this notation both in your book and in your homework, and the first time you see it, it can look like, what is that even trying to say to me? But x, as x goes towards infinity, just means as we go off towards the right, what happened to the function? Well, the function goes down. As x heads towards negative infinity, as the function goes to the left, the values go up. It's just written in a way that makes it look more formal. Crystal, does that help? It gives you kind of a way to express it very technically, but Yes, no, maybe? Yes. Okay, good. So if we go back over here and say, I want to add just one more term here. Let's say we go plus 5x to the, I don't want to use a 6. Let's say x to the 9th. Well, if we follow our pattern down here, we know it's going to have as much as, if it's a 9th degree polynomial, it's going to have as many as 8 turns. It could have less. And as many as 9 intercepts. It might have less. But in terms of its end behavior, we essentially have 2 questions. Are the, I'm going to call them arms, it's not a technical term, but are the arms, are the ends of this polynomial going to go in the same direction or different directions? And is it going to, I'm going to say body parts today. Is it going to head, I'm going to say upward, or head downward? Now, by upward and downward, these all head generally upward with the wiggles in the middle. These all head generally downward. Our parabolas open upward or they open downward. So is this going to be is it going to be the arms are the same or different? And is it going to be upwardly oriented or downwardly oriented? So for this particular 9th degree polynomial, trying to figure out where all the wiggles are there is going to be a chore. But just from a perspective of end behavior, what can we say about how this is going to behave? Same or different, upward or downward? You can put them in a little chat thing if you want. You guys are quiet today. So let's ask here, what about a parabola? In a parabola, did the arms head the same direction or a different direction for a parabola when it was x squared? Yeah, different and opposites.
Different direction.
For a polynomial, they head in the same direction. For first degree, they went different directions. For third degree, they went different directions. In a fourth degree, they went the same direction. In a fifth degree, they went opposite directions. What's the rule seem to be? Odds are opposite. Crystal, yep, and evens are the same. Now, why is that? Because if the even powers, they destroy that idea of being negative. So the even powers take those big negative values on this end and make them positive. They take the positive values, make them positive, the negative values, make them negative. The odd powers don't do that. The odd powers take the positives, make them positive, but they take the negatives, and when we raise a negative to the 5th power, it stays negative. Now, the whole thing might flip upside down if that lead coefficient is negative, but they still head in opposite directions. So, yep, the 9th is going to be different directions. Is it going to head generally upward or generally downward? Up towards infinity, Aaron, up towards. So Aaron, why up? What told you that it was up? Not a negative degree. You know, be more particular here. Not a negative lead coefficient. Yeah. But yeah, this was a positive, so it's going to head upward. If it was a negative, it would head generally downward. So again, we don't know where the wiggles are, but we know this thing's overall behavior is going to be upward as it goes through its domain. And okay, however many times it ends up wiggling, it could do some weird wiggles. That's a whole nother subject, trying to figure out where those wiggles are. But it's nice to be able to look at just this big nasty ninth degree polynomial and go, okay, there's a lot of stuff we don't know yet, but we do know its overall look. And one of the, I'm going to say, fun things is if you zoomed out enough on what this graph looked like, this graph looks like that. If you zoom out long enough. Okay, right in here, if you zoomed in there, you'd see wiggles. But most of this graph's behavior is just that kind of almost linear growth with some wiggles right in the middle. So yeah, we usually care about those wiggles. It seems like we haven't analyzed a lot because we don't know about those wiggles, because those are usually what's modeling what we care about. But frankly, we know what almost all of this thing's domain is, except for just a little part in the middle. Questions about that? This is going to be especially helpful when we start trying to pick out where some of the x-intercepts and so forth are. Because if we're trying to graph a polynomial and we know, say, it has those x-intercepts, if you want to draw a polynomial that goes through those x-intercepts, well, we could either come down this way or we could come up this way. How are we going to know which one of those to do? We're going to know which one of those to do because we know the lead coefficient and the lead term. So it's going to be, helpful in how it tells us how to start and how to stop. Fun. It's just a blast, right? Yeah. Okay. I am going to give us a nice little polynomial here. Say x squared minus 2x minus 8. If we had this polynomial, it is a quadratic to start us off nice, then we could do a lot of things. We could certainly talk about its end behavior. The ends are going to head in the same direction and they're going to head upward because it's positive. We also could tell things like where its y-intercept is. Its y-intercept is going to be at that's y. Sorry. The y-intercept is going to be at that nice -8. But if we want to try to tell things like where its x-intercepts are, we can do things like ask the quadratic formula, and the quadratic formula is great, or we could complete the square, also a good thing to do. But the problem with completing the square and the quadratic formula is it only works on quadratics. So as we go to third or fourth or fifth degree polynomials, that's going to stop working. So if we try to use a different tool to find this thing's, say, x-intercepts, what could we do to try to break down this polynomial into something that we can look at a little more effectively or try to analyze a little more effectively and find those x-intercepts? What was one of the first things you learned how to do with something like this? Aaron jumped right to it. Yep, factor. Now, we know factoring has some limitations. It's got to be nice and factorable. how factorable it has to be kind of depends on where our factoring skills are. But we know that this factor of x minus 4 is going to lead us to a x-intercept at x equals 4. Now that's what we're used to calling them x-intercepts. You'll hear sometimes people call them zeros of the polynomial. So we'll have a 0 at x equals 4. That's just a value of the polynomial that makes it equal 0. Sometimes we'll call them roots. It has a root of x equals 4. Roots because the number that builds the foundation of the polynomial. Similarly here, this x plus 2 means we have a 0 at x equals 4. Again, could call that a 0. We could call it an x-intercept, or we could call it a root. It's all the same thing. 4, why did I put 4? And nobody yelled at me. It's that other 4. Sorry, at negative 2. So one of the first big theorems we're going to throw around shouldn't be a big surprise, but it's called the factor theorem. For any sized polynomial, doesn't have to be a quadratic, for any sized polynomial, if x equals a is a 0, if it makes the polynomial 0, again, we'll often call it also a root. If it's a real number, it's an x-intercept. If x equals a is a 0 or a root, then x minus a is a factor. And if x minus a is a factor, works in both directions, then x equals a is a 0. Or again, a root, and if it's real, it'll be an x-intercept. So going between these factors and these roots or zeros or x-intercepts is going to be a big tool that we're going to have as we go through chapter 4 and start trying to build and break down large polynomials. But the first issue we're going to run into is trying to break down, trying to factor larger and larger polynomials is a bit tough. For some of us, depending on how your factoring skills are, factoring even a quadratic might be a little bit tough. So we do need to practice those factoring skills. But we need to kind of broaden out how we go about factoring to make it work in a more broader, more flexible way. So how do we factor? When we factor anything, what are we doing when we factor? So one of the examples I like to give is if we just want to factor a number, say we want to factor 51, or even ask if 51 has any factors. We certainly know it's not divisible by 2, so 2 can't be a factor because it's not even. But if somebody suggests, hey, maybe 3 is a factor, how would we test to see if 3 is a factor? What would you do to see if 3 was a factor? Let me know in the chat or just unmute yourself for a minute. How would you check to see? Yeah, the way we check and track down factors is we try division. So we'd say, hey, can we divide this 51 by 3? 3 goes into 5 once. 3, 2, 1. So 3 goes into 21 7 times. Hey, and that's exactly 21. So the division, not only did the division show that 3 was a factor, it also told us what the rest was. It also told us what the other part of that factoring was. So we want to use that idea of how do we factor stuff? Well, technically, when we factor, we're dividing. We want to use that to start trying to break down polynomials. So if we had a large polynomial, let's not go too crazy too fast. Let's say it was x to the third plus 2x squared minus 6x minus 4. If we had this third degree polynomial and we want to try to factor it, we could test to see what might be a factor of this thing. So if somebody asked, say, is x minus 2 a factor, that's essentially like asking over here, was 3 a factor? We tested it by dividing. Well, we're going to test polynomial factors the same way, by dividing. Now, somewhere back in your careers, you have hopefully seen good old polynomial long division. Same process as we did over here. It just looks a little bit different. Okay, it can look a lot different, but it just looks different. But if this divides with that 0 remainder, then we know that x minus 2 is a clean factor of the polynomial. Not only that, we will be left with a second degree polynomial. So we'll have broken this third degree polynomial down into 2 smaller pieces. And that's generally going to be our goal. So maybe we remember how to do polynomial long division and maybe we don't. But it is something we want to practice and probably haven't practiced in a while. So let's run through it real quick. It should mimic this fairly well. So we asked, what do we have to multiply by 3 to get 5? Excuse me, actually, we probably asked, 3 goes into 5 how many times? But we're really finding a multiple. What can we multiply by 3 to get as close to that 5 without going over? We're going to ask the same question over here. Don't worry about the -2 for a minute. What do we have to multiply by that x to make this x to the third? Well, we have to multiply
X squared.
Yeah, by an x squared. So x squared times x will give us that x to the third. Now, just like over here, that 1 had to be multiplied by the 3, this x squared does have to be multiplied by the entire x minus 2. But we just use the lead terms to make our decisions. Again, they're the ones in charge. So x squared times x minus 2 is that nice x to the third minus 2x squared. And just like over here, we subtracted that 3 from the 5, so we have to subtract these. This is the step where things sometimes go wrong.
Yeah, I was about to say I always found it helpful to put parentheses around it.
Absolutely. Either I like putting the parentheses around it. Some people like to distribute that negative automatically. There's one of our colleagues in Grants Pass always says, when you draw the line, change the sign, because it rhymes and people like rhymes. So whatever it takes to have you remember that this negative has to be distributed through this whole thing to perform that subtraction, however you like to denote that, great. Just be careful about it. So these will subtract away perfectly, the x to the third minus x to the third. These should always work out nicely because we made our choice based on that. But this +2 minus -2, that is going to give us a +4x squared. And then I'm going to bring down the -6x and leave the -4 for there, or for a bit. Okay, then we continue, just like here. We left with the 21. We asked the same question again. What do we have to multiply by the x to get 4x squared? Well, we'd have to multiply it by a +4x. Notice I am putting the x squared and the 4x in line with the other x squareds and x's. That is a handy habit to be in. But that 4x times the x is going to give us a 4x squared, just like it was supposed to. And then negative 2 times 4x is what, negative 8x. But again, we have to remember to subtract that. So the x to the fourth, or the 4x squared and the 4x squared cancel out. They're supposed to. When that negative distributes, we're going to get negative 6 plus 8. So we're going to be left with a positive 2x. Bring down that negative 4. And we're almost done. What do we have to multiply by this x to get a 2x? Well, a 2. 2 times x minus 2 is 2x. And is it really minus 4? Did it really work? Again, we're subtracting those, so be careful about the signs. 2x minus 2x is 0. Negative 4 minus negative 4 is 0. So is x minus 2 a factor? Well, we got that 0. It divided perfectly. So yes. And if that's all we were asked, then fine, that's all we were asked. But what did we also learn? We learned that this polynomial is equal to x minus 2 times x squared plus 4x plus 2. So we not only did we find a factor of this, we found another factor of it. So great, we could continue trying to break this x squared plus 4x plus 2 down, or noticing that that is a quadratic, if we wanted other x-intercepts, we could even use the quadratic formula on that, because as soon as it's down to a quadratic, let your quadratic skills take over. Well, gosh, now I want to know. That would be 4 plus or minus the square root of 16 minus 4 times 1 times 2 all over 2. If we tried to set that equal to 0, so 4 plus or minus the square root of what, 8? Yeah, over 2. So 2 plus or minus the square root of 2 over 1. So we'll get a nice 2 plus or minus the square root of 2. So if we tried to graph this, we'd have one x-intercept at positive 2. 1, 2, so right there. We'd have 1, 2 plus the square root of 2. So square root of 2 is about 1.5. So 2 plus 1.5. So that's going to be our 2 plus the square root of 2. That's our 2. Again, it's about 1.4-ish. So 2 minus the square root of 2 is going to be about 0.6-ish. So it's going to be right there at 2 minus the square root of 2. So we've got those 3 x-intercepts. It's a third degree polynomial with a positive lead coefficient, so we know how it behaves. So we know it's going to look like that. Oops, sorry. We even know it's got a little y-intercept down there at negative 4 because of that negative 4. Questions about that?
I mean, how do you know where to graph the square root? I mean, you're just going with the 2 part and then the rest is like whatever is after the decimal?
Yeah, I'm just approximating that. It's 2 plus or minus. I have the, the square root of 2 is more than 1, less than 2. If you want to be more precise, it's about 1.4-ish. So I just said it's about 1.4. So it's 3.4-ish. And when you subtract them, you get 0.6-ish. So, you know, between 0 and 1, I made a dot somewhere, you know?
Yeah. Okay.
So no precision in there at all. And even just, you know, knowing that that's, you know, certainly has to be between 1 and 2, because 1 squared is 1, 2 squared is 4. So it's got to be between 1 and 2, means it's going to be, you know, between 3 and 4. So between 3 and 4, we put a dot.
Okay.
How do you know what's a good binomial to try to divide it by?
Right now, we don't. In a section or so, we will learn a couple of tools to generate some good proposals. So we're going to come up with a list of here's good things that might work to try. But at first, in this section that we're about to do, in the section after that, we're really going to be at the mercy of having something else say, hey, here are some suggestions. But we will grow kind of past that. But even before we do that, the section we're at right now is going to be a nice review of this good old polynomial division skill. So we're going to spend a section kind of practicing that. So, you know, given something like, you know, 4x to the 5th minus 2x to the 3rd plus 6x squared minus 4x plus 1, if we wanted to try to divide that by x squared minus x minus 3, practicing being able to perform that division is a goal that we have. We want to get fairly good at doing that. Now, some of you have done synthetic division. We'll talk about synthetic division tomorrow, or I guess not tomorrow, I guess Monday. But you've probably seen some synthetic division in your background. If not, you can look at it, and we'll talk about it a little bit on Monday.
But a lot faster.
It can be a lot faster, but it has a huge disadvantage. It doesn't work when what you're dividing by is larger than a first degree polynomial. So in a case like this, it would be impossible to use a synthetic division. Well, impossible is a strong word. Luckily for us, as we go through the rest of chapter 4, we are mostly going to be testing linear factors. So we'll mostly be doing dividing into or dividing by first degrees. So we'll be able to use synthetic division a lot. But there are going to be a couple scenarios in chapter 4 where we're going to need straight polynomial long division, because we're going to be needing to divide by larger things. And as you go along, this skill for polynomial long division, dividing larger things, is going to come up. You know, this is one of those skills that comes up kind of every once in a while. So it is something we want to make sure is in our kit. Just like completing the square. It's one of those things that doesn't come up a lot, so it's easy to kind of leave behind, but it's going to start coming up, and this is going to start coming up often enough that we just want we want to make sure we're more familiar with it than a lot of folks are. Fair? So take just a moment. We're kind of out of time. So go do that division, practice. You can find some videos on polynomial long division. If you need more information on long division, let me know. But this is a chance for us to practice it, because we are going to use it in the rest of chapter 4. Okay. Anything you guys need?
Nope. I gotta run to class. Have a good day.
You too. If any of you are a little more sketchy with polynomial long division and want more, let me know. But look it over. We'll talk about it a little bit more on Monday. And have a wonderful day.